Good afternoon. Welcome to today's Liftoff webinar, brought to you by LIFT, the National Advanced Material and Manufacturing Innovation Institute, where we drive American manufacturing into the future through technology and talent development. LIFT is a public-private partnership where we convene and connect government, industry, and academia in the fields of advanced materials, manufacturing processes, systems engineering to enhance America's manufacturing competitiveness, national economy, and national security. Thank you for joining us today. Today's presentation is brought to you by Miller Electric. Andrew Fuller will be presenting today. And today we're going to be talking about the importance of handheld lasers and the game-changing precision fabrication. So welcome again, Andrew. Thank you for joining us. I'd like to remind the audience in today's presentation, please make sure during the presentation, make sure you add your questions. Andrew will be taking those at the end of the session. So Andrew, take it away. Andrew, 1 second. This is Christine. I think we're having some technical audio difficulties, and I want to make sure that we hear all the great information that you're sharing with everybody. So if you don't mind, we're just going to do an audio check one more time. No, nothing yet.
Now?
There we go. So you might want to head back a couple slides and start over. Thank you so much, Andrew. Take it away.
So as I'll start back at the beginning. So laser welding has been in the welding and fabrication space in an automated sense for a number of decades, but the handheld laser welding is a newer innovation or introduction into the industry. When we look at the main building blocks of a system, we by and large could think about this like an industrial MIG welding or a gas metal arc welding system where we have a power source that delivers our energy. We have the shielding gas in order to protect the weld puddle. We also have the wire delivery system, and then the components that the welder themselves would be interacting with. Some of the things that come into play when we talk about the handheld laser systems is the safety. And so we do have the additional environmental interlocks, which we'll touch on more as we go through the presentation today. For those that maybe don't know what a laser is actually an acronym for the light amplification through the stimulated emission of radiation. Essentially what we are doing to really break this down to a very simple level is we're taking light energy similar to what you may have done in grade school, where we are
Well, Andrew froze here in the Midwest, it is really cold outside. So Andrew, are you back?
Focusing on energy, maybe we probably took. Typical arc welding processes, you're going to have an extremely high amount of ultraviolet light, which is what, when you go to the beach, is what causes sunburn. And then we have our visible spectrum, red, green, blue, that we see and perceive as humans. The welding lasers typically are going to play up in what's considered the infrared spectrum. So that's going to be anywhere from the 750 nanometers on upwards. And the handheld laser welding system that we produce here at Miller, and most of what exists on the industry for the fiber lasers, is going to be in the 1070 nanometer, maybe 1080 nanometer range. Extremely high absorbency with steel and stainless steel in that spectrum. And then we also have the red guide laser to allow us, because the infrared light is an invisible wavelength of light. We don't see it as humans. So essentially, what this system is doing is it's taking all of these different pump diagrams
Andrew, you've have frozen again. I'm going to suggest
and
that
we're
you
emitting.
go off your camera to save some of that bandwidth for the amazing content that you're presenting. Could you go off camera?
Okay, are we back now?
Yes, we are.
Sorry about that.
Yes, we are.
Okay. So what makes laser welding different than traditional arc welding? Traditional arc welding, if we think about a precision process like TIG welding or gas tungsten arc welding, that has been, from a traditional sense, the more precise process when it comes to welding and fabrication, and allows us a lot of variability and forgiveness in the process when it comes to joint configurations, things like that. When we look at that in relationship to laser welding, though, we have drastically different energy density variance there. So the traditional arc welding processes are going to be somewhere in the area of 100 watts per millimeter squared, and you're going to get a little bit wider weld bead. And because it's a transfer of electrons, we actually heat the material from the surface, and the heat soaks down into the material because of that resistance to the electron flow caused by the material itself. When we look at the laser welding process, we're about 1,000 times the energy density. So when it comes to the benefits and providing the the low heat input into the component after it's welded, that all is driven by us being able to really drive power into the components at a very high rate of speed, make that weld, and not have a lot of heat soak into the surrounding material. And it also allows us to really penetrate deeply into the part, so we can avoid some of the traditional beveling processes that we had with conventional welding processes. One of the main considerations that we have with laser welding, though, as we talked about the different spectrums of light, it becomes the safety piece. This is a very critical component whenever we look at new technologies. We want to make sure that the welders and those in the welding environment remain safe. And so I'm going to spend a little bit of time today talking about that. When we look at the PPE that's required for conventional welding, one of the biggest hazards, aside from the molten material and protecting our skin from the hot surfaces, is going to be eye and skin protection. With traditional welding, we have a lot of UV light, as well as intense visible spectrum of light that can cause muscular eye strain. And if we don't wear, ANSI Z87.1 or higher safety glasses and the appropriate shade of welding helmet, what you could have if you had, let's say, an inadvertent exposure is basically a sunburn on the surface of the eye, where you have that UV light is absorbed on the front skin of your eye and causes, in the grand scheme of things, a temporary discomfort. With the laser welding system, that invisible energy does not trigger the blink reflex because we don't see it and we don't sense that as humans, that infrared spectrum of light. We only feel it as heat. With the 1070 nanometer wavelength, what ends up actually happening if you were to not have the appropriate protection, for the personnel in or around the welding environment, is that light passes through the lens of your eye and basically focuses that down to an intense spot size. So I mentioned earlier about the magnifying glass melting, melting bugs or starting paper on fire in grade school. Your eye is basically acting as that magnifying glass. So it's very imperative that we are adhering to the industry safety protocols and wearing the OD7 or higher safety glasses for our system, rated for that 1070 wavelength of light. There's different industry standards that exist globally. In the U.S., the most prevalent is going to be the ANSI Z130, the Z136, and in there we have to look at the nominal hazard zone for skin. So basically, if you had an exposure, direct exposure to your skin or to your eyes with that laser energy, at what distances can that cause a potential injury? And now our system has different safety protocols in place, but that's something to be mindful of in the event of a worst case scenario. So the laser system that we are manufacturing can cause skin hazard out to a 53 feet. And because your eyes focus that energy down, we could have potential eye injury, worst case scenario, out to 755 feet. And this is kind of all previewing, notifying of worst case scenario before we talk about how, laser welding, we want to do some guarding. The first level of protection, of course, is going to be our safety glasses. We want to make sure that we're protecting our eyes for the wavelength of light and the power densities that are being produced with the system, whether it be a Miller system or a different brand of handheld laser. The first thing is looking at what is the wavelength and then the optical density. A lot of the PPE that exists in the industry for the laser protection is going to have multiple different ratings. So you see this particular set of glasses had 2 different ratings for the different optical densities, or basically how much power it can filter out. And we want to make sure that it has that 1070 nanometer rating at OD7 or higher. If a company, for example, has a CO2 laser cutting table in their facility, those are typically going to be in the 10,000 nanometer range, as opposed to the just shy of 1,100 nanometer. And so that PPE may not be suitable for protection for the handheld welding. And that's what a laser safety officer in that facility is going to have to make that determination. The next piece is going to be the laser welding helmet, which is going to have additional laser protective lenses. And then, of course, whenever we're dealing with hot or molten material, we want to be protecting our skin with appropriate welding gloves and jackets and safety toes. Because this energy, can emit for some distance, the industry standards, the ANSI standards, specify that we need to either provide PPE for anybody within that nominal ocular hazard zone, or we have to put up some protective barriers. So there are a number of different barrier manufacturers that exist in the industry. This particular one that we have featured on the screen was manufactured by Kentech. There are others, Laser Vision and so forth, that offer different levels of laser protected barriers and different configurations that can be customized to a manufacturing environment. Essentially, you don't need to buy it pre-produced. Here in Appleton, in our facility, we have a brick room. The door has interlocks installed on the room, and so if there's an existing portion of the facility that can be utilized, this can be accomplished in multiple different ways. I've seen as far as with some companies where they turn the entire facility into the laser controlled area, and they have procedures or protocols in place where the laser welding operations are only taking place on second shift. So there's multiple ways to accomplish that laser controlled area to satisfy the industry standards. Being that we are melting material, melting metal, whenever we have a welding operation taking place, we want to make sure that we're extracting any potential vaporized particulate or fume, weld fume that's generated. And we've gotten the question quite a bit of, well, does laser welding produce a smaller fume or particulate than other welding processes? And what the studies that we have performed have found is that the welding particulate from laser welding is of similar size and characteristic to that that's produced with other more conventional welding processes like MIG, TIG, or stick welding. And so typically if you have fume capture devices in your facility for conventional welding, typically that is going to be considered acceptable for the use with a laser welding process. But as always, it's best to have an industrial hygienist come in and find out if your fume extraction is sufficient for your operation. When we look at some of the safety functions that are built into a handheld laser welding product, there's kind of a couple different categories. One is going to be this first slide that I'm showing here. These are going to be the bare minimum that are required by the ANSI standard. The power key, so that's basically a way to turn off the machine and prevent unauthorized use. So the laser safety officer should be controlling access to this key to prevent somebody that doesn't have proper laser safety training, prevent them from utilizing the machine. The e-stop, which is going to allow the termination of the laser output in the event of an emergency. And then the last one here to satisfy the base industry standards is the method of preventing that laser energy or that potential scattered light energy from leaving the laser controlled area. And that's done typically through the door interlock systems. So if you're looking at getting into handheld laser welding, this is going to be 3 things that you want to look for as a base to make sure that any product you're considering has at least these, because this is the minimum industry standard. So now getting into the fun stuff. As we look at the different applications that exist in the industry and where can laser welding be used, laser welding is pretty much able to be used on any material that can be welded with conventional fusion welding processes. So the most common in the industry are going to be the mild steel and stainless steel. We look at some nickel alloys like Inconel, things like that, potentially for the aerospace industry. Galvanized, it works very well with galvanized because it's such a low heat input process. So any duct work or products that maybe are going to be manufactured for outdoor environments, we have that low heat input helps prevent the excessive burn off of the zinc and the galvanized materials. Aluminum, again, aluminum is very highly heat conductive and can sometimes be difficult to weld with conventional processes, especially when we look at thin aluminum. And then you look at other materials like titanium, brass, copper. You can even do dissimilar materials. Like if you imagine like a really high end, kitchen accessories, a lot of times you might see like copper to stainless steel. That can be done with this system. And then when we look at what is a typical system, 2000 watts or less capable of doing, our particular system, you can do down to 20 gauge, maybe 22 gauge material, and then we can do up to 3/8 of an inch thick in a single pass. I would say the sweet spot is really going to be in that 1/16 to 1/8 inch thick material range. And then when we look at the joint configurations, that's where it starts getting really fun. There's a lot of different configurations that we have, and it's important to be mindful of how we design parts to be conducive for handheld laser welding. A lot of manufacturing for conventional welding processes might have gaps or might have edge prep like a bevel put onto a component, because we're adding a significant amount of filler metal to those parts with conventional welding, where with laser we're more trying to use the substrate of the original base material in order to provide the strength to our weldment. So if we look at like the lap welds or the lap fillet type configuration, we can do through sheet, what I've heard people consider or call stake welding, where we're essentially doing through sheet seam weld of one sheet into the other sheet. Or if we just simply want to tack it before we do the fillet weld on the edge. We can do outside corners. Now, outside corners, we would typically want to try to provide some sort of a break on that component, so we have definitely have a backer behind there, because the laser energy is so efficient at penetrating into the material. If we have a gap between the two parts, that laser energy can cause excessive penetration or essentially shine through the part. When we look at more of a kind of a, you might say, a structural member in like a lighter application, sheet to tube. I've had a number of different companies that I've worked with that have been looking at moving away from like a resistance spot welding operation and moving to the handheld laser, because now, as they call it, it's like a electric nail gun is kind of how they described it to me, where they can come through and they can tack the sheet onto a tubular frame member from one side without having to have access to the back for that resistance spot welding operation. And then if we look at the right-hand side, of course, a fillet weld, those are readily and easily accomplished with this process. And if you do a double-sided fillet weld, even though the external leg size is smaller, we can actually provide a significant amount of strength, because now we can penetrate into the component and get a lot of, you might say, theoretical throat into the base of the material, versus having that external gusset that causes the distortion in those joint configurations. So where does the benefits of laser really come from? Like I said, if you have a traditional TIG or MIG welding process and you have that external large leg size, for example, when steel solidifies, it shrinks about 10%. And that's where we get that distortion. You have a lot of torsion or torque as we move away from the neutral axis of the component. And when that weld solidifies, it causes that pulling effect, which causes the member to basically tip. With the laser, we have a lot less external reinforcement, and we're relying more on the internal reinforcement. And that puts the weld metal or that molten solidification area closer to the neutral axis of the part. And also, because we have less heat soaking into the surrounding material, because the process is much faster, we are limiting the amount of heat in the component, all of which contribute to the minimal distortion with the laser process. So if we look at these three diagrams are showing both a lap fillet configuration as well as a butt weld configuration with the different welding processes. The top one being a 16 gauge material, MIG welding. You can see there we get penetration to the root of the weld, and we have quite a large weld bead. TIG welding, because it's such a precise process, we can very intimately control that filler metal to heat delivery ratio and get a you might say a more adequately sized weld. And then with the laser welding process, we can easily capture that root and put a nice square plug of penetration into the part without causing a lot of distortion. And then the bottom members that you see there, again, the same thing, MIG, TIG, and the laser processes. With the MIG welding and the TIG welding process, we're essentially required to bevel the components in order to get that same weldment stacked in there, where with the laser welding process, we can easily accomplish that with the amount of penetration that we get into the component, and significantly reduce the prep time, the weld time, as well as the heat put into the part. So as much as I like to talk about where laser welding is great and how it's can significantly improve some of these operations, I also do like to focus on the fact that laser welding is not for every application. It's not necessarily ideal for a number of different places. The first thing that's really going to be a driver behind that is the amount of filler metal that we're providing or depositing with the handheld laser process. With our system, we're depositing about a half a pound per hour. I've seen some systems in the market where they might be running multiple wires. Realistically, you're still sub 2 pounds per hour, typically sub 1 pound per hour of deposition rate. And when we compare that with conventional welding processes, a typical mature or proven out MIG welding operation should easily be depositing 15 or 16 pounds per hour. So we definitely want to consider what is the result that we're trying to get by looking at a new technology. If we're doing a weldment where there's high cyclic loading or notch effect, where there's maybe larger gaps, and we need to fill that gap in, that's going to be something where traditional welding processes like MIG or TIG might still be ideal or more suitable. And laser welding, even though you could do multiple passes, we're still only depositing a much smaller amount of filler metal than with those other welding processes. And then the other thing to consider is if it's an outdoor environment, so like constructing a building, for example, because we have that we have to construct barriers or protect those that are not involved with the welding from that potential scattered or emitted laser energy. It may become more complex to ensure the safety of those individuals. And so for the most part, the handheld laser welding up until this point has been mostly implemented in an indoor manufacturing or fabrication type environment where we can have static containment with barriers and walls. It becomes, like I said, much more difficult once we start moving outdoors. The handheld laser systems typically also have a cleaning component to them. So this can offer quite a bit of benefit to an operation over conventional cleaning processes. There's both cleaning that you can do prior to welding on the components or the parts, and you can do cleaning post-weld. So coloration removal, for example. So the pre-cleaning of the part prep, if you have a component that has some rust or scale on it from sitting for a period of time, we can actually just switch the nozzle of the laser delivery apparatus and switch the mode, and easily clean or strip that rust off of those components. Now, when we look at some of the benefits there, the ongoing or the replacement costs of abrasives, one of the big things is whenever we're using rotating abrasives of, the send off or the cast off with potential wires from a bristle brush, that grinding dust that is generated and all the mess that creates. A lot of times you might have joint accessibility issues where getting a 4-inch or a 7-inch angle grinder into a component in order to clean the rust off of it can be cumbersome, or if you have complex profiles, that can become cumbersome for a tack welder or a welder in order to be able to access. With the laser energy, if you can see it, you can clean it. And so as long as we can satisfy that nozzle safety contact, that allows us to clean the components and strip that rust off. And then post weld, this has been a big one for the stainless steel industry, whether it's manufacturing components that go into aerospace or food and beverage industry. When we weld on stainless steel, it's not uncommon to get that bluing or that straw discoloration as the material oxidizes outside of the shielding gas as it's cooling down. With the handheld laser welding, whether it's welded with the laser system or whether it's welded with conventional TIG processes or conventional MIG processes, we can utilize this to go through and strip that coloration off. We don't need, pickling paste, which is really being cracked down on by the EPA. We don't have to have, electricity and acids and processes that generate, high amounts of hydrogen, which can, create their own safety implications in an enclosed space. So this can significantly reduce the amount of time to clean up a weld after the weld has been created. I'd like to take a couple minutes to talk about some different applications that we've seen where the laser has provided significant benefit. The first one is going to be the emergency apparatus, truck trailer, like truck body industry. So a lot of these companies are building basically aluminum cabinets, and it's not uncommon for this industry to use a push-pull system with MIG, and a lot of these industries, because of the labor shortage, have gone to simply doing intermittent or tack welds to hold the body or the cabinet members together, and then gluing them or sealing them up with some sort of an adhesive. Now, we had one company in particular came into our facility that when they onboard a new welder, they have them go through like a practical welding test where they actually give them an assembly to test not only their welding ability to see what the resulting welds look like, but also their fabrication sense to make sure that they can actually put a part together or a cabinet together and have it be straight when they're done. And ultimately what ended up happening is if they don't weld it correctly, the part twists and the last couple parts don't fit. They were able to accomplish this with the handheld laser system. They welded it what they considered the wrong way. They didn't have any of the burn through heat signatures on the backside. And they got to the end and all of the components still fit, even though they didn't follow what they considered their typical fabrication routine. And they were absolutely amazed with the fact that now they can take somebody with little to no welding experience, little to no fabrication experience, put them in and have little to no risk of burn through heat signatures on the backside of the component. And now they can potentially eliminate all those adhesives because they can weld it complete and get that hermetic seal through the weld versus through adhesives or sealants. Another application would be the agricultural space. this chipper chute that you see on the right-hand side of the screen, even though, that little bit of distortion that's present in that assembly doesn't drastically impact the way the wood chips are thrown either into a box truck or out into the forest. That is something that, cosmetically for a very high-end brand like Vermeer is something that, they want to try to minimize. And so by implementing the laser system, that allows them to drastically reduce that distortion, that oil canning effect where the parts just twist all around, and gives their brand a much higher perception in the industry simply because of the reduction in distortion. Now, there's some other secondary benefits that have come along with an application like this, where if you have components that are welded like a tank that's welded onto a frame member that's been intermittent welded in the past, when that goes through paint, that paint doesn't get between those members, and on a product that lives outdoors, that can create problems long term where water gets in between those unpainted surfaces and causes corrosion issues, which either will cause long-term reliability issues with the device, or merely just a perception. And again, with a very high-end brand like that, perception can go a long way with the value of the product. So really, when we look at the value that the handheld laser provides, just kind of at face value here, one of the big things that I've seen in the industry is that because it's a drag tip design, you can take somebody that has literally no welding experience, bring somebody from an office, or bring somebody off of the street that has no formal weld training. And we know that the welding industry is really constrained in this regards of finding skilled talent. The handheld laser really bridges that gap and allows us to take somebody with no welding experience, and within a matter of minutes or worst case days, bring them up to producing very high quality welds, as opposed to a conventional welding process. You might be looking as much as weeks. By eliminating the need for doing intermittent welding, because now it's so low distortion, we can, in many cases, and I've tested with multiple different companies, fully weld an assembly. We can do that in less time to complete the entire assembly, as well as we eliminate as much as 50% on the layout time, because we don't have to go through and mark all these intermittent welds. When we look at potential for raw material savings, I've talked to a lot of companies that are welding and manufacturing their components out of thicker material simply because they can't find somebody that can weld thin gauge material consistently. With the consistent nature of the penetration that the laser provides, we can now precisely control that. Companies are able to use thinner materials for their assemblies that are more suitable for the application, as well as they can prevent that burn through on the backside, because we are precisely controlling that penetration characteristic. So that concludes my bulk of my presentation. I open it up for some questions.
Thanks, Andrew. Great presentation. Really appreciate it. You spent a fair amount of time talking about the safety, which is obviously really important on the laser side, the requirements, the minimum requirements needed from the industry standard perspective. So thank you for sharing that. And it was also interesting how, as you said, handheld is not for everything. The traditional, welding processes obviously are relevant as well. So again, thanks for the great presentation. I'm going to get started with some of the questions if you're ready to begin.
Yep,
So, is, as on the safety side of it, here's a question on the code side of it. Is the handheld laser in any of the AWS codes?
So as of right now, there's not in the handheld laser welding is addressed in um, within the AWS through the C7 specification, as well as other specifications for automated. Being that handheld is more of a semi-automatic welding process, that is kind of a new space. I'm actually working. I sit as the chair of the AWS D17, which is the Aerospace Fusion Welding subcommittee, and we are working actively to incorporate provisions in our next revision for handheld laser welding. So that would go through the weld qualification, like the procedure qualifications, how we qualify the welder, and how do we ensure that the people utilizing this process across the board, so they don't have to self-qualify it on their own, and they can more easily implement the process. I know that there's the agricultural industry and the construction industry has been looking at this. A lot of people using sheet products are looking at this. So we are actively working with the AWS to try to get this incorporated into the codes and specifications because it is not addressed today. Although there are a number of different manufacturers in various different industries that have self-qualified this and are using it in their operations.
Thank you for sharing that. That's pretty important. I guess as a chair on that committee, you will ensure that it is addressed and it is, complies with those codes. And as you mentioned, those industries that are really, it matters to those industries. So appreciate all the hard work that you do on behalf of the industry to ensure that gets across the goal line. So thank you for that. How about, you talked about this, but is there anything else you want to expand on, the replacing of the MIG and TIG welding? Like I said, you did touch on it in your presentation, but is there anything you'd like to expand on? Will the handheld laser replace it?
Yeah, that's a great question, and we actually hear that every so often of a lot of people that have whether they're a welder or a supervisor. It's always a concern of is this new technology going to take my job? Looking at putting yourselves in a welder's shoes, and I kind of attribute this similar to automation. Automation has its place, right? It's a great tool for a business to use to be more consistent, more profitable. Automation is not for every application. The handheld laser welding, I would say, is very similar to that. It is a great tool to have in a company's repertoire where they can utilize it and utilize it appropriately, but it's not intended, or I don't think the technology is really there to replace a lot of the traditional welders, which are more of a skilled trade. And most companies have enough workload of specialty applications that they would rather expand their workforce, bring somebody in with little to no welding experience to utilize the handheld laser because the learning curve is so short. Utilize the handheld laser for some of those easier operations where you're doing, either repetitive welds, longer welds, where the laser can be applied easily and effectively. You're always going to have an application where there's poor joint fit up. There's going to be a gap. You need high deposition. That's where you want to maintain your existing workforce for those higher, I guess you might say, higher profile or applications that take a little bit more of that craftsman tradesman skill set, and kind of use the handheld laser as an expansion or an extension of your existing workforce by utilizing it in the easier applications and keeping the existing workforce for that overabundance of the skilled, maybe harder applications, you might say.
Okay, so, and I appreciate the reference to the automation side and the clarification as how important it is to not replace the MIG and the TIG. So I have a question, another question regarding the strength. So with laser welding being such low heat input, does it have strength and penetration?
Yeah, so as some of the slides that I showed, you don't get that external leg size that's commonly associated with conventional welding processes. And typically weld strength is going to come from, a certain PSI over the cross section of the weld. Basically, your throat dimension is going to be your weakest component in most applications. And because we don't have that large external leg size, it's often perceived that laser welding is not as strong. And because it's so low heat input, in many cases, if people watch videos of it, they go, well, there's no penetration there. It's so low heat input, there's no penetration there. And the cut and etches actually prove otherwise. We actually can get significant penetration into the members. And in, let's say, a steel application, you can actually get, significant strength from your welding joint because of that, you might say, internal reinforcement of the weld. It's not an external leg or external gusset that's causing distortion and also strength. We're relying upon the base member as well as a little bit of supplementary filler metal. When we look at applications, I don't think we've necessarily done the studies on this yet, but if we look at like an aluminum application, aluminum in many cases, when you weld on it with conventional welding, your heat affected zone becomes the weaker component because how the material is essentially annealed. And if we have a reduction in heat input into the component, one can argue that you might actually get, for throat dimension compared to throat dimension of laser welding, you might actually get an increase in joint strength just because we're not compromising the surrounding base materials.
Thanks for that.
So by and large, I would say comparably, you're typically going to see as good, throat versus throat, you're going to see as good or potentially better joint strength than conventional processes.
Appreciate that. So how new is this technology? I mean, obviously, if you're sitting on the chair of the standards, and how new is this? How game changing? Obviously, it's game changing, but it's relatively new. Can you talk a little bit about that?
Yeah, so laser welding has been around for decades. Handheld laser welding first came into the market about 4 or 5 years ago. It has slowly been becoming more mainstream. At FabTech this year, there was certainly an abundance of different solutions, some providing more safe options than others. But I would say in the past, let's say 2 years, and that's ultimately why the welding standards, whether it be through the AWS or API, ASME, any of those, that's why we don't see provisions in there for the welding standards, is because it is such a relatively new technology, and those standard bodies or committees oftentimes aren't going to take the legwork to come up with a new criteria for a cutting edge technology until there starts to be implementation of it in the industry. And we're seeing such a large influx with industries, like I said, everything from agriculture all the way up through aerospace, that there's a lot of governing bodies that are looking at adding provisions in to allow or account for the handheld laser processes.
Thanks for that. Obviously, the implementation and adoption is very important. So so that wraps up the Q&A part of it. Great presentation today. Obviously, this presentation will be available following this. We will send out a thank you to everybody and appreciate everybody joining us. So Andrew, great job. Miller Electric, thank you for your membership and your contribution here at Lift. We do appreciate it. I'd like to tell the audience our next, to mark your calendars for our next Liftoff webinar, which is February 26th. Wenzel America is going to be talking about the science of precision metrology and how it's driving modern manufacturing excellence. So I appreciate your expertise today in sharing this and all the good work you're doing on behalf of the industry. So Andrew, thank you very much. And thank you everybody for joining us. Have a great day.
Yes, thank you everyone.